It's a simplification of underlying maths and computational modelling has recently actually won some awards, including the UK AMC and the SIAM UKIE. Apologies if I've said any of those abbreviations poorly. And he's interested in using 3D printing to create new types of cellular structures for engineering next generation smart materials. Let's welcome Alex, that sounds awesome.
Hi everyone. So today I'm going to talk about initially the cells in like fruits, and then we're going to go on to kind of more general cellular structures, so things like the skin and the heart, and then we're going to go on to the materials that we're trying to make in engineering to have like special properties for applications such as like making bicycle helmets. So it's good to start a science talk with an experiment. Now, this is the cells of a potato, actually, and what you have is each cell has like a cell wall that's really stretchy. We have something inside the cell, and then we have cohesion between the cells, so the cells can separate away from each other. Now, different things that happen to, say, apples or potatoes will change the way that these parameters interact with each other. So here I've got a fresh apple. I have an apple that I put in the freezer overnight, and it's now thawed. And then an apple that I put in the microwave. And I don't recommend doing this because it starts kind of popping and exploding. So the fresh apple, it's really firm. It's like if you bite into it, you can have that kind of fresh, juicy texture. And what happened to the frozen apple is like it's gone really soft. Like the whole thing is really squidgy and juicy. And what's happened is the liquid inside the cells has expanded in the freezer, and that's then broken the cell walls. So it's just a sack of fluid now. And the same kind of thing seems to happen in the microwave, but it is more firm than the frozen one. So it seems that all the way through the frozen one, it's become soft, whereas the microwave one, it's only like the top and the bottom that seem to have really gone mushy. So to kind of show you a little bit more about what's happening, we're going to hit it with a hammer. I haven't tested this. This is science. We're going to see what happens. But my hypothesis is that this one's going to crack into, like, say, two main pieces, and these ones are just going to kind of smush.
Are we ready?
No. This is the most important.
So maybe need to kind of practice the swing.
Yeah, whenever you are.
Right. Cool. So that's fallen into like some main chunks, and there seems to be quite straight lines where you've kind of ripped through the material. So now,
This is the ex-frozen apple.
this is the ex-frozen one, yeah. Okay, so it's mostly held together. It hasn't like flown out anywhere, but it's a bit grim, to be honest. It's all a bit discoloured inside, and it looks a bit like a peach. So for the microwaved one. That once again looks a little bit discoloured, but not as bad as this one, and it's less juicy. It kind of bit squishy. Right, so the main kind of takeaway thing from this is that when it goes under different conditions and the different kind of parameters change, like the cell walls either break or they stretch too much, it changes the global behaviour of how the material works. And we can try and understand these parameters and hopefully then try and utilise them in engineering to make new materials. So I look, in my PhD, I look at the mechanical activity that's happening. So I don't really care about what happens with the chemicals. It's just, the chemicals change the way that the mechanics react. So either, when you bite into an apple, you have the cells burst, and you get all that fluid released in your mouth, and it tastes beautiful, and that's what you want in an apple. Or if you get an older apple that has been, say, like in the fridge for a couple of months, you find that it like falls apart in lumps. And what's happening is it takes less energy to separate the cells than to burst them. So to highlight this, we have two balloons that have been glued together. So I'm going to pull at them, and there's two options. Either the balloon's going to burst, or they're going to peel apart. And I've got no idea which. Okay. So it took less energy to burst the balloon than to separate them. Because if it was a weaker glue, then maybe they would have just peeled apart and balloons would have been intact. So just to highlight, like this is wood, and either we can crack through the center of the cells, and that's them bursting, or we can crack between the cells, and that's the same as like debonding. And generally that's only going to happen if the cell walls are thick enough that it can kind of support that crack that goes through it. Now, when I started my studies, I deal with solid things, and all the other people in the applied maths group deal with fluids. Yet we use the same kind of mathematical analysis, or very, very similar. And someone said to me, do you actually know the difference in between a solid and a fluid? Now, a fluid is like a liquid and a gas, and as the name suggests, it can flow. But the way that he described it to me, a solid has a sense of memory. When you pull it, it remembers where it came from. Whereas a fluid, when you push it into a certain place, it only knows where it is now, and it will carry on from the kind of the easiest path to take. Whereas the solid wants to pull back to where it was. And, well, this is what I studied. So, if you have lots of cells, we can arrange them in different ways. When we have our like simplifications, either we can have them in like a square packing. So this is an example that someone in engineering uses at the moment, where we have all the cells kind of just on top of each other in a line. Or we can use some sort of like staggered packing. And generally, as you can kind of see, if you've got gravity working on these as well, as soon as one of these cells kind of goes out of place slightly, most of them are going to end up stacked like this. In the same way when you've got lots of oranges and they're all kind of arranged, they're all at this offset position. Because there's, well, it's got less space, like airspace between them, but it's just a more stable place for it to live. Now, here we have like a point contact between each of the circles. If we were to like suck out all of that extra airspace, we end up with hexagons. And hexagons are mathematically proven to be the most efficient use of like the smallest cell wall material for the amount that it can store within it. And that's why bees use hexagonal patterns for their honeycomb. And this is the structure that I fundamentally study, what happens when this structure deforms. Now, this is the most efficient in 2D, but if you were to look at 3D, what is the best shape to have lots and lots of these things where you've got the least amount of wall space for the amount of stuff inside? And that turns out to be the tetracadodecahedral cell. And you can stack lots of them in space. I just like it because the name's really nice. So when we deal with the contact of stuff, we have to treat it mathematically. And don't worry, this is the only maths that's involved in this talk. We need to make sure that when we've got two objects, they don't pass through each other. So you've either got a positive distance between them, or you've got no distance between them. And then we also say that either there's a compressive force, so I'm pushing down on the table, or there's no force at all. Like, as soon as I try and apply tension and I pull my hand up, my hand just leaves the table. And this problem was attacked by, well, first posed by a guy called Antonio Signorini. And the thing in mathematics that we really care about, or some people care about, is a problem well posed? And that means, is there a solution? Is there always a solution? And if so, is it unique? Because you can have multiple different solutions. And this is something that people worked on for years and years, and finally, someone came up to Signorini and said, yes, it is actually well posed. And amazingly, well, not amazingly, but he actually died very, like a couple of days after finding out this information. So this was a really big thing in his life that got concluded before the end. And it's his mathematics that makes the fundamental part of what I study. Now, this is one of my structures. We've got hexagonal cells, and to simulate cohesion between the cells, so like some sort of stickiness, we say that there's a pressure that pushes between the cells. Now, to check that this is like any sane person, you need to check it against the normal validation cases. So we compress the material, and yes, it acts like a honeycomb would when you compress it. And when we put it in tension, once again, it's kind of bowing in on the sides, as you'd expect. Now, we also have shear, which so for this material, I can either pull in tension, I can compress it, or to shear it, I'm pushing one side one way and one side the other way. And this corner and this corner are getting closer together. So they're in compression. In the same way, this corner and this corner are getting further apart, so they're in tension. So let's say these cells can separate. Where do you think the crack will occur in this material? One good way of doing a little test for yourself is if you grab your shirt and you pull it one way and push it the other way. You notice there's some rolls that occur, and then it's also being pulled in the other direction. And that's kind of what happens in this material. We have these diagonal cracks that open. And as we vary the cohesion, as you'd expect, the stronger the cohesion, the smaller the gap, and the more it kind of sticks together. Now, we then move to looking at more complicated structures, where it's really hard to actually make a simulation that actually has results when there's so many cells and so many different complicated different parts, that we end up working out what the mathematical equation is that explains the whole thing, and we just make this simple little unit. And it makes it so much easier to calculate what happens when we deform it. So here we have like the red is like a high stress, so we're pulling this structure up, and the blue is a low stress, so it's not really moving laterally that much. It's all in this direction. And our multi-scale model gives us the same average stress over the structure, but it's much easier to calculate. And this is really good in terms of, it makes complicated things more accessible to engineers that can then kind of take a real material and fit the data of that material to a model that is then kind of easy to calculate. So, we've got a cat picture. And this kind of analysis of cellular structures is really good for having a look what happens in the paw of the cat, or what happens on the sole of your feet, these little fat pads that are constantly getting used, and it's good to understand how they deform so you can make your feet last longer. But also, it works in the brain. And the way something that's being studied at the moment is when you go for an MRI scan, you're laying down and your brain is kind of sagging into a certain position. And they scan your brain, and then when you stand up again, your brain's in a different position than it was when you were lying down. So the results from the MRI aren't necessarily the same as in real life. You could have a pressure that only happens when you're standing up. So these kind of models can transfer the information from when you're lying down to then the information when you're standing up. So, moving on to engineering, one thing that's quite popular is biomimicry. We have a look how things act in nature, and then we make things that work in a similar way. So this chair has this kind of same pattern as wood, and these different cells in the wood mean that when you sit on it, it's comfortable, but also it's made out of one thing all the way through. There's no cushions on it. The whole thing is kind of half cushion, half structure. And with 3D printing, we're starting to use cellular structures to not only reduce the amount of material we use and the amount of printing time, we can actually make flexible parts because they can kind of be changed in a certain way so it deforms as you want it to. So here we've got two things that look identical, but when you compress them, one of them turns into a smiley face and one turns into a sad face. And we can even make things like door handles. So changing the kind of rotational force into something that's pulling out that way. And there's so many possibilities of what we can do in the future with this kind of material. We can make so many different things from these interesting, complex structures. So these are a few that are kind of special because most structures, when you pull them in one way, they get thinner. Whereas these structures have a negative Poisson ratio, which means that, like this structure, when I expand it, you'll find that it just expands in all directions. And this is really interesting because if you get an impact on something, or it gets pulled, the cells can kind of work together in this cool way where they can just help deflect the force into somewhere else. So this is quite an interesting area of engineering research at the moment, and one that I'm really interested in. Because, well, we can make some sort of like shock impact protection, and this is like an example that was made in engineering recently of something that they're using in bicycle helmets. Now, part of my passion for this comes from I designed these structures, and I want to understand how they work and can we apply them. Do they actually have any like real life applications that can justify us researching them and someone giving me money to study it? Now, what I believe is that because these structures are flexible, like here, I can squeeze it quite a lot and it's going to return to its original shape. Can we use it for vibration dampening? Can we find specific types of vibration that this will filter out, which means that, say, if we have an earthquake and there's a certain frequency that makes the building just get really excited and shake a lot, can we filter that out in the concrete at the bottom? Because it would be useful. Now, the thing about them is that you can make them into like pyramid shapes. And then the pyramid shapes you can connect together in different ways. And you can make things that look like cubes, which will stack up quite nicely. Or you can make them into, okay, such a tetracadodecahedron. So this will stack in 3D space. You can have just lots and lots of these. Or you can make geodesic curved surfaces that are reinforced. And I have stood on this before, and it took my weight, but that's why it's a little bit flat now. So I don't really want to do that again. Now, I've recently started like studying these structures with universities, so we put it in a machine and we pull it, and we have a look at like where these points are getting displaced, and then we build a simulation, and then we can compare the results between the simulation and the real life example. And I'm very lucky recently that I've got a new collaborator who understands a lot about vibrational analysis. So we're going to be moving forward and understanding the behavior hopefully quite soon. Now, the thing about this structure that isn't to do with its actual performing properties at all, it's just a purely because it's pretty thing. It's based on a branching pattern. And as you can see when it's branching out, each part's getting smaller and smaller. And when the parts get smaller, using a number called golden ratio, which appears in many places in nature because it's got some really interesting like growth properties, you end up with an outline that I think is beautiful. And it has a couple of different names, like it occurs in different ways when you have a look at the growth of trees, if that branches out in the same kind of way. But also, the algorithm I used to generate this, I ran it backwards. And I ended up with this pattern that's in the center as well. So, thank you for your attention. I'm glad you enjoyed what I've talked about. Yeah, thank you.
Thank you, Alex. That was awesome. And I've been doing this for about 18 months. I've never seen so many props on stage before. So just well done for being able to handle them all at once. Have you guys got any questions for Alex?
Can I have one? How easy is it to make those models you have? For, well, any of them, I suppose.
So,
Apples?
Well, the apples maybe as well.
The apples I just bought from the reduced section. These I had to weave by hand, so this one took maybe like 6 hours. This one took maybe 30 hours. That one took maybe about 100 hours. Well, it was a good commitment for my time. But then the 3D models, once I had the geometry on the computer, I could just press print effectively and just pay a little bit of money, and then this would come out of like a big bed of powder, and I can make exact versions for a cost, but with relative ease.
How much did it cost to make each one of those?
So say this one's about £8. This one, which is a miniature version of this, was about £25.
What did you pay? Is there a place in the get
Yeah, so I use a website called Shapeways. And you just need to use some software, and there's freely available software on the internet that you can use called OnShape. Build a model, send it to Shapeways, just upload it on the website, and they give you a price. You can scale it, select different materials, and then in a couple of days. Yeah. So in the last few years, just the accessibility of all this kind of 3D printing stuff is just it's at our fingertips now.
You do a lot with hexagons, and of course the material of the future is graphene, which is based on hexagons. So does your work inform in any way the kind of structural properties of graphene? And if you printed these things out of graphene, it'd be like indestructible Minecraft, wouldn't it? You could just build structures that would be pretty much indestructible and could just fit together really easy. That's a Buckminster Fuller geodesic.
Yeah.
So it's all just the future happening there, isn't it?
We are lucky in terms of the technology is just about ready to give us so many new possibilities of what we can do, and now's the perfect time to make designs to try and utilize that. In terms of these structures, it would be amazing if graphene can not only be like really strong, but vibration dampening also. Because there are so many different structures that are currently available, like the hexagon pattern, like this is just like honeycomb. If you put 2 sheets on either side of it, the strength of this is incredible. And they currently like use this kind of thing for graphene, and like I'm told that it takes my body weight, but it's so light. So structures like this are the first ones that they're going to use for graphene. Now, in terms of understanding graphene, there's kind of, like my main area is, they call it hyperelasticity, which are things that can really, really stretch. Whereas graphene is very linear in terms of its properties and its breaking point. Down the line, hopefully there is some good crossover, but currently the way that I analyse my structures and the way they use graphene is...
So when you shear just a sheet of it, that's not really like you shearing a bee honeycomb or something like that? Not enough to inform it.
So, in terms of like when we have the crack that can open, honeycomb won't do that because it's easier for the cell wall to fail. But if we set the cohesion to be strong enough, then it acts in exactly the same way as honeycomb. So we can, a honeycomb is something that we can effectively model with this. Right. We just need the right understanding of the material parameters for the cell wall, and then we put it into the model and it will work.
So, with the aerospace industry recently developing that material that's considered almost lighter than air, but structurally quite sound, these structures that you're creating, in terms of kind of like weight ratio to strength ratio, will that be kind of along the same lines, or will it be a step forward from there? Or?
So now, is the material you're talking about super stiff, or is it one of the ones that can be fully compressed and then back out again?
Yeah, fully compressed, but when they drop it, it kind of almost floats down because it's kind of surface is obviously distance compared to the air. So it floats down like a feather, but has the same kind of strength that it can obviously go back to its original shape.
So that one has really special properties. It's called a pentamode, I believe. And that can be fully compressed down and then it'll go back to its original shape. This, if I stand on it now and compress it down, it's going to end up kind of just a mush at the bottom. So that one has a much larger resistance to high forces, and it is lighter for the strength. But the selling point of this compared to that is that the vibration dampening capabilities. That one is going to be the main kind of future material that is going to be used. So I don't want to say that this really compares, but I think it's hopefully going to hold its own in some way. Different purpose, yeah.
So if I understood well, you're trying to reproduce living tissues into, well, you're trying to reproduce living tissues. And I think you can either like do like vegetable structures or animal structures, like more rounded or more hexagonal. So which one do you think is more useful for what you're trying to do?
So the first part to talk in terms of the mathematics of it is just trying to understand the principles of how they work. Whereas when we get into the engineering part, we generally look at really complex structures that couldn't occur in nature. We're trying to learn from the way that, say, apples or whatever works. In terms of understanding the more complex things, I believe it's more like the vegetable and fruit tissue, because of the fact that the cells contact with each other. They're separate cells that contact, whereas in like skin, it's fused. So if you rip it, it's always going to be the cells ripping as opposed to peeling apart.
So that extra thing of contact is something that definitely happens because, say in this material, when I compress it enough, different layers contact each other. So that's where the kind of maths of that comes into this. Any more questions?
I'd like to say a massive thank you to Alex.